All right, everyone, welcome to the mini tutorial on an introduction to uncertainty quantification. I'd like to introduce our special guest, Dr. Roger Ghanem. He's a professor of civil and environmental engineering at the University of Southern California, where he holds the Tryon Chair in Stochastic Methods and Simulation. Dr. Ghanem's research is in the general areas of uncertainty quantification and computational science with a focus on coupled phenomena. Please welcome Dr. Ghanem.
Good morning, and thank you all for being here. And thank you, Kelly, for inviting me to talk to you. So, uncertainty quantification. It's a very interesting subject. It has allowed me over the past 40 years to take a ride through much of science and technology and engineering. It's almost the glue that allows us to ask useful questions, and I hope to convey that perspective to you today. So this tutorial will have three parts. A big part of it will be to look at a number of applications of interest, to see the diversity of questions, of perspectives needed to talk about uncertainty quantification in a useful fashion. The second part, I will talk about, based on some of this diversity, I will try to noodle out some requisites for what it means to do good modeling with uncertainty quantification. And then I will share with you some of the things that we are doing in my group that I think are at the forefront of these ideas. Please feel free to interrupt at any point. We have people online?
We do.
Okay, good. So, applications of interest. So, this is one of the first applications I use in my presentation. This is a very old slide, but it's still very valuable, and excerpts from published emails in connection with Columbia's last mission. Okay? And if you squint very hard, you'll be able to see this. Right? So the text says simulations showed that landing with two flat tires were survivable. So they were exploring multiple ways to recover the shuttle, and they did simulations on the biggest computers with the best models, and simulations showed that they could land with two flat tires if that was needed. But Bob and David expressed skepticism, even though they had those simulation results, that based on some data, they did not trust the simulation results. Right? So I think this highlights very striking, I don't want to say urgency, but usefulness. This tension between packaging what we know into computer models that can do predictions, and then having in the back of our mind something that we learned from data or from other experience that challenges that knowledge. Right? And we keep seeing this over and over and over in almost all the applications that we encounter. So one way to think about this is to say, well, this is what the simulations gave us. This is our best guess at what reality is. This is what reality is. Reality will happen. There's nothing uncertain about reality. It will happen, right? Single, unless you believe in parallel universes and you put a probability distribution on those. But reality will happen. This is our best guess at that. And then these are the things that make our best guess different from reality, right? This is not a mathematical statement. This is more a logical statement, if you want. So I was trying to think about what makes our prediction different from reality, right? And then you start thinking about what would it take, who should you hire, where should you invest in order to bridge this gap, right? And then you would want to invest in bigger computers, You would want to invest in better statistics. You would want to invest in more experiments. And you may want to invest also in looking deeper with better science at atomistic scale, perhaps, or better models. Right? So there's a whole sequence of investments that allows you to bridge the gap between your prediction and reality. And this is where uncertainty, useful description of uncertainty, can come in. Right? So this could be a point estimate, and this would package the credibility of this point estimate as it attempts to describe that reality. So this has been my plan for the past 40 years. I'm not close to characterizing these terms, but I think it's a useful path that can help us understand the value of information, the value of investment in each of these components here. And these are these errors here are conditional errors, right? So given a model, then you assimilate data into the model. Given a model and data, then you do statistics. Given models, data, and statistics, then you do numerics. Okay, so these are not just adding big computers with big statistics with big data. You have to put them in the correct conditioning sequence in order to feed into the overall prediction. Here. Okay. We will come back to this slide in a little bit later. So some examples. This is a fuel canister for spent nuclear fuel. It's about this big. And while it's being transported, it's important to know before it's stored in salt mines for the next 10,000 years. You do want to be able to ascertain its condition. What does it look on the inside, right? And one of the dangers is that while it's being transported, it may be subjected to an accident where the insides could be mangled in this fashion following an accident. And you would want to characterize to best of your ability the inside of this canister without opening it because it's radioactive. Okay. This is what it looks on the inside. This is the canister. There's this basket on the inside, and this grid here, in each of these grid cells, one of these assemblies is inserted, and each of these assemblies has about 90 fuel rods inserted in. Okay, so it's a fairly complex object. You cannot open it once it's sealed, but you still want to be able to, after you've transported it, to ascertain the condition of what's inside. Okay, so you could flip a coin, or you could go to school, get 2 or 3 or 4 PhDs in different topics, and or you can listen to this talk. So this is one of the challenges that one has to deal with, that brings out uncertainty about many things, right? But we don't have time to describe those particular things. Another application is trying to design a scramjet engine. Right, this is what the flow looks like. This is one of the fanciest simulations of what combustion looks like inside scramjet engine. So let's pretend this is reality. This is what things look like really on the inside. It's very complicated. Bless you. But we see this on a computer. You never see this particular shape of combustion in a real engine. What you see in a real engine is this is an experiment, right? This is the model of scramjet. Flow goes from here, comes out on the other side. It's instrumented with sensors at different locations on top. This is the top view of the sensor location across and along the length. So we have very finite number of sensors on the wall of the engine in an experiment. But this is what the flow really looks like. And the danger of stalling, the danger of losing thrust, is really something, is related to something that happens on the inside, not on the wall. But the only access we have during an experiment is to the wall, right? And what we would like to do is, these are, and if you take measurements on the wall, then the measurements are never the same. There's a scatter in the pressure, temperature, and heat flux measured on the wall, right? So you don't have a single record to back engineer or reverse engineer what's happening on the inside. There is uncertainty in the measurements you take. And your objective really is to do a design optimization. You want to find the best shape and profile of the injectors for the engine so that you minimize the risk. So you want to minimize probabilities of bad things happening. You want to minimize the cost of running the thing, right? So you have probabilistic constraints, right, under very limited data. Your data comes from measurements on the wall. Evaluating these constraints involve running computer models that have hundreds of millions of degrees of freedom, so they take a long time to run. So these are some of the challenges, and we know there is uncertainty. We don't have enough information, but even if we did, it's very expensive to implement any of that into our computational workflow. Right? So this brings the need for reduced models, for scratching your head to simultaneously on the statistics side and the numerical side, okay? to enable this optimization under uncertainty, right? So you have one loop here for optimization, another loop for uncertainty, and then each entry in that double loop is extremely expensive. Another application, and I have a choice of application that tries to highlight or underscore different challenges associated with uncertainty quantification and trying to perhaps motivate some of the current research directions in this area. So another interesting application is when you string together manufacturing with performance. Right? So you want to design, this is for composites. We don't want to just design the composite material itself. We want to design the manufacturing processing for composites so that the composite as designed performs in a certain fashion. Right? And this is becoming more feasible now with additive manufacturing technologies, where you can design the additive process itself so that the finished project or the finished product has a life cycle performance as intended. Okay, so in a composite, for example, you start with a flat sheet, you drape it, and as you drape it, you create kinks, even very tiny kinks. And then as you inject the resin and the resin flows and hardens, those kinks create heterogeneities that eventually are going to be the points where cracks and damage nucleates. Right? So discovering where those kinks and heterogeneities are really allows you to, or is related to the manufacturing process. If you can model that, string that together with performance, then you're in business. But folding any sheet of paper or fabric or whatever the shape of the folded product is going to depend very much on the variability of the fibers being folded. And no fiber is identical to another fiber. And it's that heterogeneity in the fibers and their ondulations, right, that's going to create, right, this is a folded sheet, and you see a variation in the colors. Right? These variations were the result of the folding process. And it is these variations that are going to create, as you inject this, the resin is going to sort of try to navigate around this heterogeneity and will eventually create, as it hardens, it will create softer spots that will be magnified as you load the piece. Okay, so that's how the fabric gets. So that's again another source of uncertainties. Now, if you take this piece after it's shaped and hardened and you slice it, that's what you see across the cut. So there is significant heterogeneity in the layering of the composite. The black areas are resin. The whiter areas are resins that are oriented at different angles. But you see the shape of the resin. Sometimes they're connected, sometimes they're not connected. And this creates big uncertainty in how the composite is going to behave. Right? And this is actually, this variability is what has slowed down the implementation of composite material in products that are required to withhold significant impact or force. It's one thing to use composites for the hood of a car. It's another thing to use composites for the sides of a car where you can expect side impact, for example. Okay, so this variability limits the reliability of the products being produced. And understanding how to control it or live with it and mitigate it is important. Right? Another application is different but also very common. These are oil wells in the Gulf of Mexico, producing oil wells. And let me see, what's the next slide? At each one of these, now the oil companies have detailed almost X-ray vision around each of those wells. But BOEM, the Bureau of Energy Management, offshore energy management, at each of those wells has a table that looks like this. Right? So we have a table of about 120 entries at each of the wells. The table describes the type of rock, the depth to rock, the depth of water, some geological properties, the color of the rock, things that may seem not very useful, but it turns out that they are extremely useful actually, because it's these things, that these additional variables that cannot be digested by a reservoir simulation code. It's those variables that really carry information about geological processes that allows you to extrapolate from a point here to a point here. Right? But we will not get into that detail at this point. But what's important in this particular application is, given that you have BOEM data at these locations, what can you say about the risk of starting a new well at this location? Right? And these questions became very important after the Horizon, forget the exact name, explosion of 2010 or 2011. Right? So people wanted to assess the risks associated with some of these explorations. And all they have to go on are data from existing wells. Right? But it's an important topic because people wanted, this is the shallow area. All of these are in the shallow water area. And so the shallow water area has pretty much been mined to death. And there's big interest in mining the ultra deep water area. Now, in the ultra deep water area, we don't have, it's the area over here. We don't have barely any data. Right? So what do you make about mining here? What statements can you make? How can you assure, how can you provide, if you want to buy insurance, how would the insurance price mining in this area? Right? If you're the governor of Texas or Florida, how can you assess the risk to your coastline from mining activities at these locations? Right? So the question is, this was a project we did for BOEM. What's the risk associated in mining away from this coast, given that this is the data that we have? Okay, now, when you first started this, I thought it was a big stretch. Of course, short of a rational answer, they have to flip a coin, because they have to mine in this area, whether we want it or not. The question is, can anything we know about science, data, engineering be useful in helping, guiding them reach a better answer, right? Even an epsilon better answer would be very useful. Turned out actually we could do quite a bit more than just a tiny bit, and it all lied in the parameters here that we initially thought were useless. Because it's those parameters really that encoded the geology that is not relevant to an oil company. An oil company cares about the immediate neighborhood of a well. And that's only 6 of these numbers that carries that information. Okay, so again, that's an important type of question. It's not, this question here is not about a bigger computer. It's about knowing how to read data. So it's actually about data science. And of course, there's this is not the cross section of the Gulf of Mexico does not look like this. Okay, this is a caricature of what it may look like, and the oil reservoirs are these yellow patches here. Okay. Now another example is example suggested to me by Kelly. This is Enceladus. It has jets of ice particles of water coming out of it, about 100 jets on the surface, and they know there is potential life in these jets. And JPL wanted to plan a mission at some point in the past, I'm not sure about the details of this, that intercepts the jets and comes back with 2 grams of stuff from the jets. Now, this is not on Earth, it's not on the moon, this is on Enceladus, it's the moon of Saturn. Right, so you want to plan a mission that goes over there, intercepts the jets, and come back with 2 grams of stuff. Many things could go wrong, right? The jets may have died by then, right? Or the jets actually change orientation. So there's big uncertainty. It's a very expensive project. Given who we are as humans, I think we will have to do this at some point, right? But you can imagine the uncertainties in sending something over there to traverse jets that we know not very much about, and to come back with 2 grams of stuff. I mean, it's hard to imagine what 2 grams are, right? But these are problems that we are more and more frequently being faced with. Now, you take this, you turn it around. Now, instead of the jets going up, the jets are coming down, and you have a problem of plasma physics, right? So this is a jet of, we're firing plasma onto a substrate, supersonic firing. The distance is about that much. It's not planetary distances. And the objective here is to create a nanometer, micrometer scale layer on the surface of the substrate that would protect, this would be the inside of an engine, that would protect this during hydrogen combustion. And what you want is you want to create a layer that is very thin, that has some particular morphology, that has these columnar structures, because the columnar structure is going to protect the engine. It's going to actually facilitate the thermal management on the surface of the engine. Okay. Now, we don't know. I mean, you can imagine we have no control over where the particles of this suspension are going to land. It's highly uncertain. And it depends very much on how fast this nozzle is moving in this direction and the distance of the nozzle from the substrate. Right? And if you end up with a cover that's amorphous, that does not have this columnar structure, that it will not be effective at thermal management and at protecting the oxidation or reducing the oxidation process in the substrate. So there are many parameters in this manufacturing process that will affect the life cycle of the engine as it's going through hydrogen combustion. Okay. Again, the experiments are very difficult to perform. Not very difficult, they're time consuming, and we were able to, this is a collaboration with General Electric, we were able to have maybe 80 specimens. But the parameter space is much larger, is quite large actually. And 80 specimens barely place a point in that large parameter space. So again, here the objective is to optimize the manufacturing process in order to lengthen the life of the engine. And in this case, bigger computers are important. More data is important because the computer models are quite wrong actually in most cases here. They're invariably missing some key physics ingredients. But they give us nice pictures. It's a good prior. Okay, good. So these are the examples. I think they cover a wide enough range to make you realize that uncertainty quantification is not about solving one equation with some random parameters or some random forcing, or it's a wide space. The uncertainty comes in many different guises and forms, and the questions we care about are also very varied. So when you scratch your head and you try to think a little bit out of the box, and turns out that, so here I came up with another example, right? So you have hurricanes coming, you're expecting hurricanes, and you're an insurance company. You want to mitigate for hurricanes, right? So you develop, I don't want to scare you, a sigma field, right? A set of events. These are all the possible hurricanes that could come, right? You're an insurance company, so you are planning for future hurricanes. So these are all the possible hurricanes that could come. And these are all the possible combination of insurance claims, right? One of those will happen, not all of them. But you don't know which one of them will happen. And you don't know which one of these will happen. But this is really the setting that we like intellectually to think about. There are things that will happen and things that we care to mitigate. Okay? These events we can call them what we observe, and events we care about. Now, very often we invent causal relationships between the hurricanes and the cost, although there may be some other effects that play a role here, right? But these events have not changed. Now, what we add to the mix is we try to think about some relationships that map these events to those events, right? For example, a hurricane comes, we have a certain number of steel buildings, concrete buildings, wood buildings, and you have maps like this that tell you what to expect, or the hurricane has certain wind speed, and it affects different types of buildings of different elevations differently, and that helps you develop some map from here to here and back. So we add this to the list of events we care about, right? But it's still a very complicated map because these events are very complex, and those events could be even more complex. So what we do is we add a mathematical suit, if you want. And instead of the real events we care about, we create a grid, mental grid, if you want, of events we know how to deal with, right? We put ourselves on the real line, for example, or in some Euclidean space, and suddenly we have a grid here and a grid here. But by putting the grid, by grid I mean we limit the set of events we want to consider. We eliminate things, and these are not tail events. These are things we are no longer going to consider. They are completely out of scope of the models we end up dealing with. Okay? And those could be very important events that you have ignored. But we almost never consider these things that we left out. And we end up mathematically dealing with nice sanitized models that we call mathematical models that we work with. And this is the starting point for most of the research and technology and everything we do in uncertainty quantification. Now, there's hope with new paradigms in AI and machine learning. that have not been corrupted by the way we do things, that maybe they will pay attention to some of these things because they are not limited by the Cartesian way of thinking that we tend to follow. But we have not started that path yet. Okay, good. So I think these are important challenges if you're trying to deal with problems where the consequences can be very significant, right? The things that you omitted from the book. All right. Sorry. I tell my students we're professors, we love to talk, and sometimes I forget the time. We're still good on time. So a modeling perspective. So given everything we've described, let's think a little bit about some modeling challenges. So we'll come back to this. Okay. And I call, given that you fix the model, right? If I'm interested in bending this, and I want to know under what force I'll break it, right? I can describe it using a beam model, which is the simplest model I can come up with, right? Or I can describe it using atomistic simulation model. So given the model that I choose to describe, to come up with the maximum force on this before I break it, right? Given that model, there's a limit on how far that model can go. And as I change the model, that limit will change. So this summation here that says how much data I have, how many Monte Carlo samples I carry out, for example, how much is my mesh refinement on finite elements, for example, right? The combination of these, if I know how to quantify it, in other words, if I can understand the error associated with mesh refinement, right? I reduce that to the maximum possible. I reduce the error with this to the maximum possible, and the error with that to the maximum possible. That describes the limit on predictability given this model. And as you change the model, that limit, you expect it to change. Now, in a scientific setting, we like to think that as you refine the model, as I go from a beam model to an atomistic simulation, that the error is going to go down. Right? We like to think about that path of better science means better prediction. It's not always the case, but that's for another time. Okay, so good. So we're still interested in this, and let's see what it takes to talk about this model. Right, so to tackle that, I had 4 errors. Well, it's Bayes meeting Turing meeting Gödel. Right, I'm going to start with Gödel actually at the end. Maybe it doesn't make sense to predict certain things. Just because we write a statement that we want to predict something, it doesn't mean that we have not just intellectual power, but logically, maybe it doesn't make sense to predict it. Right? So it's important to keep that in mind. Because with bigger computers and now with AI, you think that you can ask ChatGPT anything, and you should expect, maybe not with the current version, maybe we're hoping that in version 3 or 4, any question should have an answer, but that's not necessarily true. Okay, but so Newton represents, I have Newton here because it represents the fact that we have strong beliefs, F equals ma. Okay, so we do have some strong belief about some fundamental processes. Okay. Otherwise, we would not be here today in an IDA facility or with JPL or so we have been able to accomplish things with the knowledge we have today. Okay, using things based on Newton, for example. But we are starting to collect data with different sensing modalities. And we are starting to want to shoot that nozzle on the inside of the engine and achieve a nanoscale accuracy in what's coming out of that, right? And Newton does not help us very much in that. So we need to start knowing what to do with data, how to assimilate data into some fancy models. And this is where Mr. Bayes or the Reverend Bayes comes in. And then Turing comes to the help, to the rescue with ideas, interesting ideas of algorithms and computing and exascale. Okay? So we have models that we are starting to resolve with more fancy mathematical formulations, and in the process bring in more physics. We are getting data at resolutions we could never get even an hour ago. So it's the progress is very fast in getting data. There's a very strong push now in knowing how to relate the fancy models with the fancy data, right? Many big enterprises are involved in this. And we have these big computers that help with both, actually, right? But there's a caution here that there are some things that just because we get an answer, we should never forget that we have to exercise. I don't know what to call this. It's not. It's common sense. Okay. All right. Good. So the models we need models that are robust to accommodate advances relevant to we have new information in fundamental science. We have new information in technologies for data, technologies for computing, technologies for communication. So the models we have, this is a challenge. You know, our learning processes, any meeting I go to is a meeting that started many years back, and we're growing one step at a time. But this here is saying that what I'm saying here is that we need to be looking ahead and bring ideas of where technology will be tomorrow in helping us design today's models. So there's a danger in building on yesterday's models as we move along this path. And this may be actually why people like me in standard computational physics, computational mechanics have lost our shirt to machine learning, right? Because they came out of nowhere with ideas that we were not expecting, right? And we're trying to catch up with them. But this is important, right? So there are new computers, new communications. So if you're running a simulation, and in the middle of the simulation you can observe what's really happening to the real device, right? Maybe you don't need the very fancy Newton model. Maybe just an Euler type extrapolation, right? Just shooting out with a straight line, correcting with an image of the real thing would allow you to make predictions that are very accurate, right? And there are ideas, for example, the equation-free paradigms that are very important in contexts like this. So we do need models that are moving in this direction, but these models will come with their own uncertainties, right? So there's a little bit of a danger in, I'll get to that in a little bit, and well, it's not only valid for uncertainty quantification. I tell that to all my students. I haven't told it to all my students yet, but to most of my students. You know, as you gain knowledge, knowledge should never tie you down. It should open new opportunities for you, right? So as you develop new capabilities in uncertainty quantification, for example, that should not specialize you into dead ends. It should be new capabilities that you add to things you already know. And as we will see in a couple of slides, probability theory is an extremely flexible device. It has very few constraints on how to move forward with it. Okay, good. So some more guidance in modeling. So yeah, you know, we can say, for example, that the modulus of elasticity of this thing has a number, has a value associated with it. And it's a property of this object. Uncertainty is not a property of an object or of a physical system. It's a property of information. As you change information about something, the uncertainty, the probability models you have about that thing will change, have to change. And I know most of you probably take that for granted, but I'm always surprised by some very advanced people in some important positions who come to me and say, can you tell us what the probability distribution of this parameter is? There's no textbook, and they want to put those things in textbooks, publish them as properties, probabilistic properties of physical entities. Right? That's not how it works. The uncertainty characterizations are properties of the information you have. As you collect more information, the distribution will change. But it's not only the information, it's not only a matter of getting more samples. Right? For example, coming back to this, right? No, flip a coin, actually. It's easier, right? So the coin is not necessarily a fair coin. And you flip a coin and you want to characterize the probability of the coin. And of course, as you get more and more samples, as you flip more coins, you will get better idea of the probability of head and probability of tail. Right? That's one way to look at it. But if before you flip the coin, you looked and you saw whether you had a head or a tail pointing upward. So now you're adding more information to your coin flip. Right? And you flip the coin again. And now you repeat that experiment. So your information now is not just the outcome, but you're bringing in additional information. In the real setting, that information could be microscopic information, or it could be satellite information or some other information. Right? So as you bring in more modalities of measurements, the probability of a given event is going to change as well. Ultimately, as you have a huge amount of measurements, if you're taking a movie of the coin as it's going up and coming down, you should be able to tell with certainty whether it's head or tail. Right? So uncertainty is a property of the knowledge we have about that system. The amount of knowledge and the modality of knowledge. Okay, knowledge evolves, and uncertainty should evolve accordingly. Now, with one thing with the large language models and with AI and machine learning is we can mine literature for information. And this is a very active area in AI. And as you mine literature for information, you don't need to specify your stress strain curve with a formula, perhaps. Maybe you can mine the literature every time you have a value of stress to figure out the value of strain. You can come up with tables for stress and strain that are mined from the literature, perhaps. Okay, so but maybe a little bit more abstractly, if you want. Knowledge allows us to evolve grammar and vocabulary. By grammar, I mean relationships between objects can change. And instead of just having a simple input-output relationship between stress and strain, and for those of you who don't know what stress and strain is, stress is force, and strain is deflection under the force, or deformation under the force, right? So it's a simple cause-effect, if you want. But by grammar, I mean replacing that cause-effect with a graph. That's a Bayesian network, perhaps, where you bring many other factors that are significant. Maybe temperature now is significant, or the humidity in the air, right? And now instead of just stress and strain, you have a complicated set of observables that allow you to ask different questions, frame your questions slightly differently. Okay, and that is probably slightly important, I think. Right? And okay, so uncertainty reflects ignorance. And models should perhaps be able to reflect on ignorance. or on the sources of ignorance. And I'll be back to this in a little bit as well. The general area associated with this, we refer to it as modeling error. And it is very important, especially when the closer you are to failure, no matter failure of what, the less accurate and the more ignorant you are about what will happen or where failure initiates. Yeah. Good. This is an example of what I mean. This is I spent many years modeling a wing of an airplane with a shell model. And then one day I took my students to NTSB. There was a crashed airplane, and they showed us details of the crashed airplane. And this is what the wing looked like. There's a structure to the wing. It's not a flat sheet. It has a structure that looks like this. And if you look inside the structure, there are lap joints. There's glue, and there are screws and inside the wing, right? So things are not this simple. We model them as simple. But as you look inside them, there are levels of complexity. This is a Concorde or some high-flying airplane. And let me see if I can zoom in on this. I can't. This is simply, this is wiring inside the plane, right? There are hundreds of miles of wires inside the plane distributed all over the place. There are hundreds of miles of pipe inside the plane distributed all over the place. These are never accounted for when you model the mass distribution or the stiffness or the damping or the structural properties of the airplane. But they do affect the behavior of the airplane, right? Not only their presence, but they vibrate, their vibrations as well. Okay. And of course, I mean, not very few airplanes have failed since airplanes started flying, but not accounting for them forces us to stay away from an operational envelope. So we stay away with the margin of safety from an operational envelope. Whereas accounting for them may allow us to be a little bit more daring in the way we perform. Okay, so that's another type of uncertainty. And another type of uncertainty is, again, going back to this guy here, modeling this as a homogeneous material, right, belies the complexity that lies underneath. So you look with a big microscope, and this is going to have grains and crystal structure underneath. And if you look at the interfaces here where things really happen, then dislocations begin at places like this. Okay, so again, when I started my graduate studies, we all lived in this space here. Recent capabilities of sensing and computing have allowed us to operate now near this realm. This is still very expensive, but also we don't have sensing capabilities to do this on a regular basis. So the multi-scale paradigm allows us to, or aims to, bridge the gap between what happens here and things we can infer at this scale. But clearly, uncertainties here. This uncertainty, if you look at this model, you have uncertainty about the glue, about the screws, about the alignment of the lap joint. Uncertainties here are about different things. They are about the modulus, the Young's modulus, or the elasticity modulus of a shell that doesn't exist, right? So again, keeping a sanity check, common sense is important. So from this, we observe one important thing, is that mechanical properties Right? It's not just uncertainty that is not a property of things. Mechanical properties are not properties of the material, but they are properties of the model you have of the material. If you change the model, your list of mechanical properties will change. Right? So apparent randomness in these properties, right, could reflect deterministic subscale variability. Right? Again, just this is similar to saying that the randomness in the coin flip is simply because I was not looking at whether I had a head or tail to start with. As you add more observables, and the subscale variability for the coin flip was adding more observations about whether I start with head or tail. And if you want to add more subscale variability, then you observe the coin rotating in space. So as we add more information, we're looking at subscale in many cases. Okay, so uncertainty in the parameters could be due to either modeling or to specimen variability. And it is this interplay between scales and uncertainty that leads me to think that the separation between aleatoric and epistemic uncertainty is not very constructive, not in an engineering setting at least. Right? Aleatoric uncertainty refers typically to problems where you have parameters that are random. You know the model, but the parameters are random. And epistemic uncertainty typically refers to problems where your knowledge itself is uncertain, and your model itself may be variable. And I think what I tried to show here is that there's an interplay between the two. What may appear as a model error, if you look closer to it, will turn into parameter error at a finer scale. Right? So if you have the capabilities, either modeling capabilities or experimental capabilities to chase down the uncertainty, then the separation between aleatoric and epistemic is no longer as clear-cut as many people like to think it is. Good. Questions? So as I said, within the probabilistic framework, we have huge latitude to do whatever we want, as long as we don't commit these sins, or we stick with these actions. And we have a probability of the whole thing is equal to 1. And if two things are disjoint, excuse the double parentheses here. So if things are disjoint, then the probability of the union is the sum of the probabilities. We call this additivity of the probability measure, and this is finiteness or normalization of the probability measure. And we throw in a description of what conditional probability is. So within this construct, you can define this probability law to be anything you want. Okay? So we have a lot of latitude. This is much more flexible than describing how a mass, so this describes in my mind how a mass of probability moves. As long as the total mass is 1 and two masses, or the masses do not overlap and mix with each other, you're fine. This is much more forgiving than trying to describe how a real mass of stuff behaves. You have distortions that you have to describe. You have advection. You have diffusion that you have to describe if you're trying to describe how a real mass is governed by physics. So probability is much more forgiving. Probability laws are much more forgiving than physics laws. So as long as you're not violating these two things, which are very hard to violate, you're fine. Okay? So we have a lot of flexibility for modeling with probabilities. So people have been very creative in coming up with probabilistic models that satisfy this, but also are adapted to some other constraints. So we add additional constraints to this in order to come up with useful and probability models that try to describe more realistic events. So let's look at that a little bit more closely. So a standard probability course, an undergraduate course in probability would tell you that I have observations of K, and the first thing I do is I build a histogram of K from that data. Or if it's not a histogram, then maybe I build a density function, a smooth density function of K. Right? So f sub K is a density function of K. It has some parameters theta, and theta you estimate them from data. So for a Gaussian distribution, for example, this would be the mean and the variance. Right? For a beta distribution, it would be 4 parameters. And to estimate these parameters, you invoke some argument. You can do kernel density estimation. You can do maximum likelihood estimation, moment matching, maximum entropy. You can, if you have a prior, you can bring in Bayes rule. Okay, so from data, you describe the shape of the uncertainty in K. That's standard, and this should be theta. Excuse my handwriting. Okay, so this is a common approach. It ignores anything we know about K, except the data of K. The fact that we have observations of K. Now that, in many cases, it's fine if you have a lot of points about K. If you have very few points of K, then it becomes important to try to understand what is the source of that variability. Because you want to squeeze as much knowledge as you can from each data point. And one of the sources of knowledge is try to understand what is the source of that variability. And this standard paradigm does not allow you to extract, to look inside K. You just look at each K as one data point, and you put histogram over that data. Okay? So this common approach gets its constraints from the data, but it ignores anything we may know about K itself. Another set of approaches, I call them the input-output models or dynamical models. They think of K as a function of some fine-scale behavior. Okay? Well, if you're familiar with Markov chain Monte Carlo or E2 equations, Markov chain Monte Carlo, you build a chain. There's dynamics in the chain, and the output of that dynamics are samples of K. So you create a mechanism that generates K. Right? And if you have an E2 equation or stochastic differential equation, then the output you have. So I'm sorry. In the Monte Carlo Markov chain Monte Carlo, you're flipping a coin at every step, and it's that coin flipping that's going to allow you to have different samples of K. In the stochastic differential equation, you're flipping a different coin, and it's again the flipping of that coin that will allow you to generate samples of K. So there's a dynamic process where you input some uncertainty and you get as output K, as opposed to just looking at the samples of K and plotting their distribution. So we think of K as a function of some other scale, finer scale behavior, either coin flip or a white noise. That finer scale can be characterized through experiments. Right? And so in some sense, we postulate that K is a function of this finer scale. So that's another way of thinking about building a model of K. So now we blame the uncertainty in K on uncertainty in these etas. And in most cases, these etas represent a white noise process. So in doing this, we embed ourselves in D dimensions. And people who work with stochastic differential equations embed themselves in infinite dimensions, this white noise process. So when we do this, the functional form of H must be estimated from observations of K. The joint probability distribution of these etas must be estimated. But if we do this, then we would have accomplished a hierarchical decomposition or a multi-scale decomposition. We would have blamed K, the variations in K, on variations in these guys. Okay, this is similar to what I described for the composite manufacturing, where you take a sheet, you drape the sheet, you inject resin, you wait for the resin to solidify, and at the end you have a composite. You can take many specimens of this composite and break them and measure the load at which they break, and that will be a property of this hardened composite. Or in that case, the H function is the operation of starting with the fibers, draping the fibers, injecting resin, running the flow, the resin, letting the resin cure, harden, and then relax. So that would be the operation H. And these etas here would be the properties, the mechanical properties of the fibers that we started with. Okay? And the K would still be the load at which the composite breaks. But now we have a mechanistic model, a physics-based model, to relate that load to the subscale processes that are taking place. Okay. Now, I want to extrapolate this a little bit further, and going back to the oil wells in the Gulf of Mexico, right? You can imagine that the pressure in an oil well is going to depend on how the earth formed the crust in the Gulf of Mexico. So if you had a simulator that you could start with the dust coalescing and forming planet Earth over billions of years, and then the Gulf of Mexico being formed, and then something falling from the sky on the Gulf of Mexico, causing some more disturbances, another 1 or 2 billions of years, that's the operator H. So if we had the intellectual and computer capacity and the models to do that simulation, then the pressure at a point that's far out in the sea can be described as a function of that table with 200 entries, even if those entries were not relevant for characterizing the oil extraction from any particular well. Okay. We don't need to know the form of H or the value of these etas, what the etas refer to. I think all we need to do is be able to imagine that such a relationship exists. And nowadays we have machine learning paradigms that if you tell them how many of these you have, they will go out and hunt for a representation in terms of those parameters. Right? So the insight we need to bring to the table is how many parameters we think are important. And then we have automated procedures now to build representations like this. And I get back to that. We have some effective ways for doing this. Okay. Good. So this is a different way to characterize K than the preceding version I described. Okay, so now I'm going to look a little bit. So I described to you a couple of these etas. One was for the composite manufacturing. One was for the Gulf of Mexico. This is another example. This is a polycrystal, for example. And if I want to describe this material, this doesn't have polycrystals, but let's assume I had some metallic bar here and I was bending it. Then the behavior on the coarse scale depends on what happens at the micro scale, and the micro scale would look like this. And to characterize the micro scale, in other words, to characterize these variables here, I would have to perform experiments at this scale to characterize the distribution of those finer scales. And experiments on this scale would involve computing the Euler angles, orientations of the crystals within each of the grains. Okay. And that would come up with some distributions that look like this for these crystals. Here I'm showing just the marginal distributions, but you could, from enough data, you could plot the joint distributions of the 3 Euler angles for the crystal, right? And that would give you the distribution of the etas. And this H here in this particular case is, again, going back to something similar to Newton's law. You have conservation laws that relate what happens at the small scale to what happens at the big scale. Right. Now, there's one, actually, this is here is not a challenge. This is a silver lining for many problems. And that is that the things we care about typically, even though we know how to characterize things at the atomistic scales with billions of degrees of freedom, in most cases, the things that matter are very, very simple. We may have 3 or 4 or 10 of them, and typically they are quite simple. They are much simpler than the way atoms and quantum states move. So in many cases, the quantities of interest are one-dimensional or low-dimensional, very low-dimensional on the coarse scale, right? And the analysis at the fine scale, in most cases, exaggerates the complexity of the problem. And we end up solving complex problems just because we know how to do it, right? And actually, it has always amazed me that many of the climate simulations have a lot of very heterogeneous pictures on the globe and things moving up and down, and at the end, the plot that makes it to the reports is a simple plot. It goes up like this, right? So if one cares about a simple result that behaves in this fashion, there may be more efficient ways to deduce that. I've started recently talking to them about, but I think they know that. So, right. So again, this is an important thing to keep in mind. Now, this observation is extremely important when you consider optimization problems. Remember, I described the optimization of the Scramjet, where you have 2 loops, and you have huge complexity in the middle of every single simulation of the Scramjet engine. Well, if the objective function that you care about is the thrust of the engine, that's one number, right? So the quantity of interest is much simpler than the billions of degrees of freedom that go into simulating the whole engine. And if you keep that in mind, then you can develop adapted procedures that you can run almost in real time to solve that optimization problem. Okay, and we don't have time to, no, we do have some time to, I'll be getting back to that in a little bit, actually. All right, so another observation, this idea here of writing k as a function of etas, it's something that most of you have seen in your elementary class on probability, right? You're all familiar with chi-square distributions. A chi-square distribution says that a chi-squared variable is the sum of Gaussian squared. You're all familiar with a t distribution that says that a t random variable is a particular function of Gaussian variables, a ratio of Gaussian to a chi-squared variable. Okay? So we do have forms like this, simple forms, squares, finite sums, ratios, that we have seen that we work with on a regular basis as part of standard statistics. But what we need to do now is be able to generalize this away from that limited list of tabulated distributions to problems where the function f is really problem dependent and describes the physics and the data of the problem. Okay. Now, in view towards that, it helps to try to understand what eta could look like for different applications. So, for example, there is a type of distributions called infinitely divisible distributions, and a variable that can be viewed as coming out as a consequence of many small-scale interactions. So if you can take a variable and write it as a sum of other variables, that variable must have a distribution that belongs to this class of distributions. Infinitely divisible distributions. This says effectively that it's not reasonable, it's not physically realizable to think of a material property as having a uniform distribution, because uniform distributions are not infinitely divisible, and most material properties are really the aggregation of things that happen at a finer scale. So if you were to test material properties in a lab, you will always observe a tail for those distributions. They will never have a sharp cutoff like this. But you can reach a similar conclusion based on more logic-based arguments as opposed to experimental arguments. Okay, good. That's all I have to say here. How are we doing on time? Oh, there is. For each. Any questions? Okay. So we're going to move now into a few specific constructions that we've worked on in the past few years that leverage the challenges and perspective I just described for you. And these probabilistic or uncertainty models leverage structure and the data and the physics for building uncertainty, for describing uncertainty. And I'm going to talk about 3 different classes of models. One is switching diffusion. Can omit this TI here. So the other one is polynomial chaos expansions. And the third one is probabilistic learning on manifolds. So now we're going to get a little bit more specific with the technical approaches that we try to pursue. So switching diffusion, the idea is very simple. The idea is that there's something happening on top, right? And one is justified in thinking that every now and then there's a different dynamics that happens on top. And the cause of this dynamic of switching between these dynamics lies underneath. We don't see it. So every time something underneath switches colors, something above is switching behavior. Okay. Now this is typical of hidden Markov models, for example, except the difference here is that there's a relationship between what happens under here and what happens above. So they're related to each other. The first time we applied this model actually was to prediction of COVID mortalities and morbidities, where the idea was that when people were less infected, people changed behavior. And when people changed behavior, they got more infected. And you could observe actually switching behaviors up here. And if you look back at records of people's behavior, there was something underneath that was switching in this fashion. Right? So that's the idea behind the switching diffusion. We have a diffusion process that lives on the surface. A diffusion process simply refers to a Markovian process, a process that has finite memory. Okay? So we have some process with finite memory that lives on top. The dynamics of this process depends on a Markov process that lies underneath with finite states. And the switching of this process here, the transition from this color to that color also depends on the behavior above. So in other words, if I call this here x and this here theta, sorry, I'm going to call this alpha, not theta. X is governed by stochastic differential equation like this, where the drift and the diffusion both depend on alpha. And alpha itself is a Markov process, the transition of which, going from alpha at t plus delta t, from alpha at t to alpha at t plus delta, this transition itself depends on x. Okay? And I'm going to show you some application of this to a material system, where the propensity for damage depends on how much load is applied on the global system, and the behavior of the overall system depends on how much damage has been accumulated. So there's a relationship, a strong relationship, between what you observe on the coarse scale and what happens at the finer scale. Yes.
So it's actually on the last segment, but relevant to what you just said. Since I think you were saying earlier that developing models at a finer scale can be unnecessary when modeling many quantities of interest. In your experience, can modeling at a finer scale be worse or misleading understanding of the quantity of interest?
No. I didn't mean to imply that modeling at the finer scale was not needed. What I meant was that the quantity of interest is simple. It doesn't mean that you can get away with simple models to characterize the quantity of interest. But keeping in mind that the quantity of interest is simple can have important consequences on how to develop reduced models. Okay, that's a mouthful. I'll get back to that when we talk about PCE expansion in a little bit. Right, so you still have the quantity of interest that could be very much influenced by the fine scale. But the fact that it is simple means that the fine scale tells you simply that you are living in a big cube that is in 100 dimensions. The fact that the quantity of interest is simple means that you really reside on a manifold, on a very thin slice in that big complex space. And if you know that you reside on a thin slice, then you are justified in developing methods that go out to discover that thin slice. But if you limit yourself to, instead of, well, the thin slice still lives in the big cube. It doesn't live in a small cube. It's thin slice in the big cube. Right?
Feel free to follow up online if
okay. Good. By the way, an equation like this, you can always build an equation like this, where mu and b, mu is called the drift, b is called the diffusion of this equation. You can always build an equation like this with some mu and some b, so that x, as x evolves and as function of t, so that x has a distribution that matches the data that you are observing. So if you give me any data set that you have, as long as it does not have infinite memory, so any data set that you have, I can describe that data set as a solution of an equation like this by estimating proper mu and proper b from the data. Okay? This is called an Ito equation or stochastic differential equation. Now, this equation may end up having to lift very heavy weights if indeed these parameters depend on another process. And if you were to extract this process from this equation and put them in a separate equation, then this equation will be running much more efficiently. It will not have to do as complex a task. Okay? But now you have two equations that interact with each other. And you have to calibrate simultaneously the transition for this alpha and the drift and diffusion for this x. Now, this is an example of a setting where those ideas are relevant and where we have applied these ideas. These are polycrystals. So if you zoom in on most metallic systems, you'll observe something like this. And this comes from when the metals were in a molten state, flowing, and then as they started to harden, each crystal, as it hardened, was entrapped in a slightly different orientation. Right? So each grain here, each color, refers to a crystal that is oriented slightly differently relative to the crystal next to it. And depending on the material systems, copper, gold, steel, the difference in orientation can be significant or not. Right? So here we have wrought iron, powder, different additive manufactured metals. And each color refers to a different type of metal. And within each color, we have a number of specimens. So you observe big difference within between the different classes of metal. But even within a given class of metal, this curve here, for example, fails at this point, whereas this curve fails at that point. And it is the failure point really that matters. These are the extreme events. We want to be able to characterize as best we can the strain at which failure occurs, or events of early failure. These are we like for those to be rare events. Right? And this, for example, corresponds to the orange lines. This morphology corresponds to the magenta lines. Okay? And so in our mind, there's something happening at the fine scale. These grains are rubbing against each other's gently. That's the alpha process. And then when a dislocation happens, they have a big jump at one of the grains. Then you switch from this behavior to this behavior. And then when you have many grains that are jumping relative to each other, then you switch from this behavior to this behavior. Right? So this is the alpha process, the subscale process, switching between gentle rubbing between grains to one slip or dislocation, or maybe few dislocation between grains, to many dislocation between grains. Right? That's how the alpha is switching at the fine scale. And what you observe at the coarse scale is the stress-strain behavior of this collective. Okay? Now, clearly, we could model this, and in today's computers, it's not very expensive to do this, with millions of degrees of freedom. The thing is, even if we did that for one specimen, see, there is a scatter in experiments. So the only thing you know, if you got to one data point, if you simulated one of those, the one thing you will know probably is that that behavior will not happen. And the real system will behave slightly differently, or maybe very much differently. Right? So having some statistical model that can relate phenomena that happen between grains to phenomena that happen on the collective is useful. Right? So this here is a computer model, for example, that aims at describing this group here. And this red curve are the states of alpha. So here we have alpha 0 is in this zone, alpha 1 is in this value of strains, and alpha 2 is in this value of strains. And this is the corresponding x. Questions from? Okay. So, and this is the coarse scale f. Right? And once we have this model for alpha and the model for x, then we can generate millions of samples. Solving this equation is very straightforward. It runs very fast in microseconds. Right? So once we have estimated these parameters from training data, we can generate millions of these samples that describe the behavior of at the coarse scale in a fashion that acknowledges what's happening at the fine scale. So it already encodes that behavior internally. Right? So this is another place we're applying this idea. This was meant to be a movie, but it will not move. The movie will show these bright areas moving back and forth, oscillating in this direction. And there are some oscillations. This is meant to be a hypersonic engine. It's a three-dimensional simulation. The flow is going from this side to this side. And these features here oscillate back and forth. And there's some type of oscillation that when you observe is a precursor to unstart. Unstart means the engine dies. So when these guys start to oscillate in a certain regime, you know that something bad is going to happen. But of course, you cannot see this inside a real engine. The only thing you can sense on a real engine are measurements made on the surface. Right? So one thing we're working on now is to describe the measurements, sparse measurements on the boundary that we can take during an experiment as our X process that we can measure, and what's happening in the center as the alpha process, as you switch between different regimes of behavior. And the question is, by observing X, can we infer the alpha? This is by observing, which goes back in this problem here. By observing this, can we infer how much damage is happening inside the material? Translating the same question to this problem here, we want to observe the measurements on the boundary and infer the regime of behavior along the center line. Because we know from experience, from having looked at many simulations, that certain regimes of behavior are associated with failure. Okay. Good. Questions? Okay. So this is currently an active research area. And this work, by the way, was supported by the switching diffusion by the Air Force, and now it's supported by MURI also from the Navy. Active research areas is to switch with a large state space, where what's happening at the alpha state can be in the hundreds of possible states instead of 3 or 4 or 10 states. We are interested in situations where the diffusion model is not just a vector of entries, but is a matrix, has matrix values. Because, for example, elasticity properties are described as tensors, as matrices. And other quantities also of interest are described as matrices. And we want to condition on what's happening on top and infer what's happening underneath. Okay. Now, there's another, so we're done with the switching diffusion model. The other model that we're going to look at is polynomial chaos models. Now, I started working on these some 35 years ago. Every time I try to move away from them, get pulled back with new ideas, and they have been the workhorse for most of my research, and they've proven to be very resilient. So what I'm showing here is what I call a standard inference block. You feed in some input, you get some output. And in the middle, right, so the input actually could be input from parameters that specify the model, or it could be input from an upstream model, right? Very often you have a sequence of models that run into each other. So this interface here can either be another model feeding information to this model, or it could be boundary conditions, or it could be just input, an input deck, okay? Or experimental data even. So first thing you do is you look at some statistics. If you have limited data, you augment them with Monte Carlo samples, for example. You have a physics model, and you have some iterator. And these three guys play with each other. You may want to solve the physics model multiple times if you're doing Monte Carlo sampling, for example, or some other ensemble thing. So the iterator plays with the statistics and the physics model, and ultimately out comes an output. And you want typically your output to be a statistical output, either an ensemble of points or some distribution. Right? And this block here, you can put it, think of it as a building block, like a Lego block. You can take it and plug and play it many other places. All right, so let's do our budget, our error or uncertainty budget accounting as we run through this block. So first, as you bring in the input stream may have some uncertainties associated with it, possibly because the upstream model itself gave you an ensemble, right? So that brings in one, I call it a statistical degree of freedom, brings in 1 degree of freedom, or one set of degrees of freedom associated with the input stream. Then you do statistical estimation. Because you have finite samples, this brings in another degree of freedom, right? We all know, for example, that if you have n data points and you estimate the mean of the data points, then the mean itself is a random variable that that's Gaussian, has a Gaussian distribution, and its variance varies like 1 over square root of n, right? So you have here now a random variable whose strength or contribution varies like 1 over square root of n. Right? So when you do statistical estimation, you're adding uncertainty in here. Then you bring in a physics model, and the parameters of the model can themselves be random. That adds another degree of freedom here. And you may have model errors associated with the physics model that brings in yet another degree of freedom in here. Okay, and your output stream then is going to depend on the uncertainties in the input, the uncertainties that you incurred doing statistics, that you incurred with random parameters and model errors. I call all of those Xi, and the output then depends as a function of Xi. And what we want is to be able to describe in some constructive way, some useful way, this output stream as a function of Xi. Okay. So these are the stochastic degrees of freedom. And quite often, actually, the physics model is not just one model, but it's a network of models. So all of these, so you collect this stochastic degrees of freedom for all the models, and you put them in a reservoir of stochastic degrees of freedom in here, right? And the quantity of interest is Q, right? So that's how it works. Now, so I'm going to replace this block here and a little bit more. If you actually try to implement this, what you discover is that first thing you do is you take these stochastic degrees of freedom, you first map them into an input deck for your simulators, right? So these are the input parameters that go into the input deck of the simulator. And these input parameters get mapped through whatever simulations you have to quantities of interest, right? So this path here, going from these degrees of freedom to the parameters P to Q, is the path that follows physics, or physics follows whatever simulations you have. And you can call this the training set. What you want to end up building at the end is a map that takes you from these directly to this. Because this map is the map that you will use in solving these very expensive optimization problems. Right? This map here, every pass through this is going to require you to build the input deck and solve the physics problem. This path here, once you've calibrated this path, completely bypasses the physics. Okay, so in today's language, you can think of this as a neural network model, perhaps. But the requirements we have here for many of the applications we run with, the requirements are about 0.1% accuracy. We cannot afford the 10% accuracies that you achieve with neural networks, right? So this learning process have to be very meticulous. Okay. So this is what we want. Now there's a challenge. If you live in, if D is very high in the hundreds, for example, then you would need a very large number of samples to learn a map in 1,000 dimensions. Right? So that's, although this looks simple, implementing it and getting the 0.1 accuracy that you want can be challenging. So what we do instead is the following. It's reinforcement learning, or I added this after reinforcement learning became popular, but the idea is more fundamental than that, I think. So the training path goes like this and is limited by a small number of samples. Okay, so we initially build a small training path, a small sample training path. We introduce here an adaptation matrix A that transforms the initial degrees of freedom into a new degrees of freedom. Let me describe it in fewer words and with maybe a picture, a different picture. So we have the X's are describe a space. Let's say we have 3 of them, so we are in 3-dimensional space. And the quantity that we care about is aligned perhaps as a nonlinear function. Let's take the limiting case. It's some nonlinear function aligned with one vector in that 3-dimensional space. So it's a nonlinear function of x1 plus 2x2 plus x3. The question then is, how can we take this original space, rotate it so that one of its directions is aligned with that dominant direction, and then carry out a nonlinear approximation only in that direction. Okay, so we want to explore all possible rotations until we find the rotation that's most aligned with the dominant direction. And then in that direction, we want to carry out a very high order approximation. So what we're doing here is we're looking at all possible rotations A until we find the best one. And we have recipes for doing this. And then for that rotation A, we do the training. Now we're doing the training in small dimension. So it's a very efficient training that can be done here, because we've found the best rotation A. And then the eta, we're not taking all of eta, we're taking only the dominant directions of eta. Right? So here we are in very small dimension. We do this training in small dimensions, so we require a fraction of the cost. And this feedback here is the learning process for A. So once we have learned A, we complete the training, and then we build this map. And once we have this map, now going from A, we know A, so going from here to here to here is almost done in real time. Okay, so we have taken then this picture here, which is reasonable if you want, it's logical. We discovered what the computational challenges are. We built this graph and we implemented the mathematics and algorithm for this graph. Okay, and now we can handle, in most cases, almost no matter how big this dimension is, the dimension of eta is about less than 10. In most cases, it's 1. Okay, and this eta, if you change the quantities of interest, you have to recalibrate this orientation, right? Because remember, when I use this example of you are in 3D and you want to adjust so that you are best adapted to a given vector. If you change the vector to which you want to adapt, then you have to recalibrate the rotation, right? So if you change the Q to which you want to adapt, you have to recalibrate this rotation here. So that's the main cost. Okay, but we also have efficient ways to recalibrate the rotation. All right. So okay, so this the polynomial chaos expansion is actually the part of building this map here. This map is called the polynomial chaos expansion of Q in terms of Xi. So recent capabilities for this is that we can characterize probabilities of extreme events as random variables. So if you're talking about the probability of failure, for example, right, the probability of failure typically is, in many instances, people provide it as one number. When in reality, because it's based on information that could be changing, the probability of failure itself should be characterized as a random variable, right? And that's what we can do here. And we do that actually by making this map itself, instead of one map, we create a cloud of maps, a statistical map. So if you imagine a polynomial, we make the coefficients of the polynomial themselves random. So we have an ensemble of polynomials that map from Xi to Q. So we can also evaluate the sensitivity of probability distributions with respect to probability distributions. So you're not computing the sensitivity of Q with respect to K. You're computing the sensitivity of the probability of Q with respect to the probability of K. Right? And that gives you much more accurate worth of information quantities. Because how do you change the probability of the input parameter? You change the probability by getting more information. And if you're very sensitive to the probability in a certain area, then that tells you which particular information on the parameter to acquire. Okay, so this is important for worth of information evaluations. Then the PCE provides priors that are constrained by physics and data. And these priors then can be used in Bayesian analysis, and they'll be very effective in Bayesian analysis because they are good priors that have been well constrained. Okay, and the fact that we have this reinforcement learning, this feedback for A, removes the computational bottleneck. Okay. Questions on the PCE? Yes.
Are those terms, can they also be constrained by physical laws, the values of the A matrices?
Oh, very good question. Yes. The way we have it here, actually, because we only, let's say C is D, and let's say you take the first R entries in eta, then A is going to be a rectangular matrix that is D by R. Your question is, can we add more rows to A that reflect other constraints, physics constraints?
That's allowed.
That's how we would do that, right? And it's a research question, right? You could add, you could learn a, see, actually, that's one reason I use probably this term here also, right? To give it a little bit, to allow your imagination to roam a little bit more, right? So the whole point is to learn this A. Here I'm describing a linear operator for the learning. You can bring in other options as well. Now, there's, since you asked the question, there's an important, since we're doing probabilities, which is different from standard neural networks that gives you point estimate. There are little nuances that are important here. And the nuance that's relevant is the following. What I did not mention that suddenly becomes important now is that these stochastic degrees of freedom are Gaussian. So our reservoir of uncertainty is a reservoir of Gaussian variables. And all the mappings we carry out are mappings on Gaussian. So the objective becomes to shape any distribution that you want as a nonlinear function of a Gaussian variable. And that's doable. Now, the reason that's relevant here is that if you take a Gaussian and you rotate it, then you are still Gaussian, right? So as long as this is a linear operation, this is still Gaussian. If you suddenly choose to do nonlinear operations here, or if you choose the reservoir here to be non-Gaussian, then eta will no longer be Gaussian. And eta can end up with a very convoluted, strange distribution that does not lend itself to this nice graphics. Right? So if you want to put a statistical context on this, as opposed to just pushing inputs into outputs, then this is a point of consideration. Okay. Now, if you want to keep these Gaussian and this linear, just add more rows that represent more constraints, then that's does not change anything here. Other questions? Okay, good. So the last component of the work is probabilistic learning on manifolds. And the first time I worked with this was on the problem of the oil wells in the Gulf of Mexico. Actually, about 10 years prior to that, maybe 15 years prior to that, I had met Yanis Kevrekidis, who told me a little bit about diffusion maps and work he was doing on diffusion maps. And it took 15 years for me to understand what he was saying. But eventually it clicked, and turns out that those 200 parameters in the table that I showed you, from one table to the next, to the next, to the next, well, if you look at them properly, they do delineate some structure in 200-dimensional space. They are not placed at random in 200-dimensional space. The structure is impossible to visualize. It's 200 dimensions. But there are some procedures that allow you to embed that data, that 200-dimensional table, to embed it in 200-dimensional space in a very efficient and parsimonious fashion. And that procedure is a diffusion manifold. Okay? And what happens actually is the following. I don't want to give you any mathematical description of that yet, but it turns out that to compare proximity between two wells, it's not only their location in space that matters. Turns out that the location relative to all the other parameters is also important, right? And it's not only the other parameters as elements of 200-dimensional space. In other words, I did not take the 200 points as a vector and found the Euclidean distance between them. Instead, we measured a geodesic distance in 200 dimensions between those points. And if you actually follow the following sequence, you start by comparing 2 points, 2 wells, using their spatial distance. Then you compare 2 wells using the distance in 200 dimensions, the Euclidean distance in 200 dimensions. And then you switch to a third way of comparing 2 wells using the geodesic distance in 200 dimensions. Then your improvement in prediction is going to be amazing. You're going to go an order of magnitude, then another order of magnitude in improvement in prediction. Okay? So with that in mind, we were able then to adapt it. It took another 10 years. We adapted it to the Scramjet problem, the optimization of the Scramjet problem. And I'll talk about that briefly next. Okay? Oh, okay. Time flies. So prediction as a conditional estimation. So what we want is to identify, select observables from numerical or experimental campaign, estimate their Jones density function, okay, and then say, if I knew the value of one of them or a subset of them, what can I say about the other subset? Right? That's standard. Right? The challenge is, in many cases, the data is offered to us in this form. We have a table with each row in the table is an experiment, a sample, and each sample has that many features, number of columns. Okay? So you train on a sample, and then your objective is you break the number of columns into 3 groups, at least we do. One group are values that we can specify during operation. The Q are values we want to predict during operation. And the U are values that we could only observe in controlled settings. We don't care about predicting them, and we cannot observe them, right? But they are valuable for training because they give structure to the thing you are learning. Okay? And then during operation, you specify W and you want to predict Q. And you can imagine that if you have this ability to specify W and predict Q, then this can become the engine inside an optimization. As you're iterating with the optimization, W is your control variable, Q is your objective function. And then because this is a distribution, it's fairly straightforward to estimate probabilities on Q and not just numerical values. So calculating probabilities of constraints becomes also feasible and possible. So the trick then is giving some training set to estimate the conditional distribution, which requires you to know the Jones distribution. Now, if you have many columns, that requires, it's a simple matter to write that, but it would require a large number of data points. The more columns you have, the more data points you need. And the challenge is, for example, the Scramjet problem, we could at most afford 70 simulations. They're very expensive to run. For climate simulations, you could afford less simulations, right? So the challenge is we don't have enough samples to estimate this. Okay. If we did, recipe would be simple. So we do the following. I don't have too much time. We do the following. If your data came from this, you don't have enough data, but your data came from something that has structure in it, and you just looked at the data, you would not know that it comes from there, right? And you may be under the impression that the diameter of this data is that much, or the scatter of the data is that much, right? But if you had a way of gleaning, of somebody telling you, hey, the black points describe the structure, a hidden structure, then instead of this being the scatter of the data, then your scatter is measured relative to the black points, which should be much smaller scatter. And points that have data that has much smaller scatter is more informative. You can do more with it. So that's really the idea. You start with few samples, you discover a structure from those few samples, and then you generate more samples on that structure. And once you have more samples, you are back to this formula. And you can do this formula effectively. Okay, so we call this probabilistic learning on manifold. The first step is to estimate the density of your small data set. The second step is to discover a manifold, and we use diffusion coordinates to characterize the manifold, and it embeds the manifold into a vector space. Once you have discovered that manifold, we generate millions of samples on the manifold that are restricted to the manifold. So the new samples share with the old samples the kernel density, the probability distribution, and the location on the manifold. And in our mind, that manifold construction is the constraint that characterizes the meaningful constraints, physics or whatever constraints you have, right? And a simple example of what we get from that, this is the composite beam that's loaded here, and it has carbon, steel, carbon, glass, and resin. It's a hybrid composite. So what we can compute with things like this is, again, in this case, we had, I think, about 500 simulations, detailed simulations of the composite. And we can compute something like this from that. The blue curve is an exact solution from finite elements. The band that we compute here is the probability. Remember, we condition on a subset of variables, and you predict the distribution of the other subset, not the numerical values of the other subsets, right? So here we're conditioning on the values of the fibers, what kind of fibers we have inside the composite, and we're predicting the distribution of the stress-strain curves. Okay. So this is an example of the kind of predictions you can make with that. As a conclusion, uncertainty is changing its form and content as technology changes. So you cannot say I took a course in, well, the rules of probability are the same. There are 2 or 3 rules, so those don't change. But what we do with those rules, what we can do with those rules, the shape, those rules, the packaging of knowledge we can achieve with those rules is changing, right? And it has to change because technology, science, and mathematical knowledge is changing. So perspective mathematics and algorithms are keeping pace with technology and these requirements. And in my mind, one interesting and compelling objective is to reverse engineer the central limit theorem. Everything we learn in statistics is you apply central limit theorem and you go to infinity, and that's what you get. Well, we never have this. We're facing problems where we have very limited data, but we have the multi-scale, the multi-data capabilities to explore. Actually, instead of plotting a density function, we know how to describe uncertainty in terms of parameters that lie underneath. And we have the capabilities to chase the uncertainty down to wherever it's hiding. Right? So I think this is, an interesting closing point of my tutorial. Thank you.